Hello, hello. We've got a... What? Alright, sounds good. I hear myself coming through the speaker, so I think that means you can hear me just fine. Welcome to the stream. Kicking things off a little early today. Wonderful. Alright, yeah, we're going to get started pretty quick here. Basically what we're going to do, well, I had high aspirations to get this mostly set up for us so I could get through the monotonous components. I got through some of them. I've got the custom transformer wound. I've got some of the resistors populated on the board, but what we're working on today is the isolated 515 volt flyback converter. So it's going to be a lot of fun. We're going to do some line load regulation testing. We're going to be having a great time. So I'm going to keep chugging on this board and we'll get to those tests super quick. Well, at least as quick as I can. Awesome. For those that were in the stream last week, you'll be happy to know I have a better solution for the scope cam. It's not perfect, but it's pretty good. It's pretty good. Alright. So, just so you know, I was chugging through the resistors, got through a few values. We just finished up 7.5K, 110, 121. Yep. We only got a couple more left. Hey, welcome to the stream. Yeah, we're going to be populating critical components for the isolated 515 volt flyback. Hello, welcome. Thanks for dropping in. Joining us on this wonderful adventure. Yeah. For those interested in more of the line load regulation testing part of this stream, we'll get to that pretty soon here. It'll be probably 30 minutes, 40 minutes. So if you're really here for the explosions, not so much for the journey, yeah, that's about when we'll be getting to that, but cool. Yeah, let me know if you can hear me all right. Let me know if you can hear me all right. 5. Yeah. Hope you're all having a wonderful morning. Oh, yeah, for those who are on the stream, someone, I think it was No Corporation, they told me about these T12 handle soldering irons that you can get for super cheap from, you know, the usual suspects like Amazon, Alibaba, whatever. Pick your poison. Yeah, so let me know if you're interested in a review of the T12 soldering station. Right now I've got mixed feelings, but as I use it more this morning, I think we'll start to get a better idea. 104, 105. There's an art to finding parts in a sea of parts. You know what? I know it's still early, but I think we can get some sweet close-ups in here. Alright. R105, R104. Just going to show you a little bit of this close up soldering action. Actually, 105 is going to be really hard to show you, so I'm going to do 104. I set the camera in the way, putting that other part on the board. So put a little dab of solder on one pad, go in, get the component placed, follow that up with some solder on the other pad. And just make sure we get a little flux. There's, on the record, way too much solder on that component. Whoa, sorry about the earthquake. Come on now. So R104. Oh, we're so close. The cable's fighting me. Ugh. Just can't win. There we go. Hey, Mustafa. Yeah, no problem. Hope I said that right. Mustafa? Yeah. It's my pleasure. It's absolutely my pleasure to share. We're gonna have some, if that was about the tips and tricks on the soldering, we're gonna be doing a couple ICs here, like U26. That one will be a lot of fun. Yeah, nice fine pitch. Nice fine pitch, I see. Yeah, happy to have you. Okay, so there's, oh boy, I think I lost a resistor. So you got R104 and 105 down. Uh, 114, 107. Our next, there's 114. 107 should be in this region. Nope, it's way over there. Yes, an R111. Yep. All right. Oh, there it is. There's the third part. Thank goodness. Thought they were gone forever. Whoa, there's an extra. I'm gonna throw that part out. Getting little SMD parts confused can be a big issue. For those that tuned in a couple weeks ago, we were assembling these 3 buck converters. Oh yeah, I need to talk about that. I need to talk about the buck converters. I did a little bit of work on that in my free time, in my fun time. And the reason why is because, well, we left them in pretty sorry shape. Basically, we blew up a bunch of controllers, we blew up a bunch of MOSFETs. Hey, welcome to the stream. Blew up a bunch of controllers, blew up a bunch of MOSFETs. And for those wondering how many is a bunch, I'll show you in just a second. I'll grab the pile. I think we've got like probably 20 FETs. Probably 7 controllers that we blew up over the course of our testing. Like, what? That is a ton of parts. But yeah, we blew them all up, and I left the stream thinking that I understood what the problem was. Ended up diving in on my own time, and yes, our suspicion was correct. Is the peak current limit programmed into the controller? We optimized the programmed peak current limit to make sure we'd never fall out of regulation. Turns out that's not, we assumed that we wouldn't violate the safe operating area, so I'm trying to talk and solder at the same time. 99% right? Cool, that's better than 0. But yeah, the peak current limit was definitely not right, so yeah, here's the pile That's all the dead chips from debugging those 3 converters. And we're not quite technically done. So I have it debugged to the point where when we're loading it reasonably, it'll never fail. But if I do a short circuit test, it, instead of entering hiccup mode, it still sometimes explodes. So I need to figure it out. Turns out on the higher voltage bucks, we need to put a more rugged low side FET because the steady state power is well within the capabilities of these ICs, but the peak power violates the safe operating area. So we're having a bit of a explodey issue. Alright, so we got the 2.15K. Moving on up. 10K. 2 of these. We'll be done with our commodity resistors. Yeah, well, I hope you're having a nice morning. Just happy you guys could join in the shop. It's a little earlier than usual, but then again, I don't know if it's early or late where you're calling in from. I just appreciate you taking the time. 122 and 108. 122, 108. Alright. Oh, come on now. I cannot find this part for the life of me. There it is. Nope, that's C108. Okay. R122. No. Oh, what the heck? Who made this board? Oh, there it is. Cool. It's hiding right in front of me. That's alright. I'm really excited for this test. This is a converter that was designed... Yeah, if you guys want me to talk about anything in particular, just shout it out in the comments and I'll talk to it. But I'll filibuster with the design story for this converter. It's actually pretty awesome. I mean, the general idea is we need 5 kilovolt isolation from the input to the output of this supply. And the reason why is because this is the supply that's providing the gate drive voltage for our inverter stage, for the PFC, for all these supplies that are connected to high voltages that are dangerous to touch, which makes it absolutely critical that when we intend for these supplies to be isolated from me, that it is, so I don't get electrocuted. And so that's kind of where it came from. We had this problem of, hey, we need a little bit of 5 volts, we need a little bit of 15 volts, but we really don't need that much power. We just need to get some energy across. And so designed a little custom transformer that can meet the isolation requirement, designed a feedback mechanism that is not standard by any means. Oh, it's a little kludgy, but I think it just might work, and I'm really excited to find out. Apparently I lied. We've got some 100 ohm resistors to get on the board. Yeah, this is the last one. By the way, if you're curious where all these test tubes are coming from, we've got a sweet part organization rack. Check out that video. I'll throw it in the description if I remember, but I might forget. I think it was like 3D printed small parts organizer, something like that. It was a good one. Broke out the 3D printer. Got, what is it? 96 test tubes times 5 almost 500 test tubes. It's a lot of parts that we keep organized now. Super convenient. Hey, welcome to the stream. Looks like we got another person. Super cool. 115, 116. Or 116. Or 115. 123. Hey, I'm doing a good job of finding these. Yeah, so the feedback mechanism that we employed on this supply is basically a Zener diode. So there's a couple linear regulators that are actually producing the 15 volt in the 5 volt rails. But what's happening is that rather than generate that directly and have to make precise feedback, the output power is so low, we basically just do fixed duty cycle PWM control to shove some energy across the isolation boundary, and then we trim off the top with some linear regulators. But if the load on those linear regulators is so low that there's no the bus voltage starts to get dangerous, it starts to get close to the limit that the linear regulators can handle, it basically dumps that energy through some Zeners and through an optocoupler that tells the PWM controller, hey, tone it back a notch, we got plenty of power. And so it'll switch between a couple power states, like 3 different PWM duty cycles that it'll change between depending on load level. Super, super cool. So it's always trimming some power off the top with the Zeners and everything else, but I think it's pretty cool. I think it's a pretty novel or unique or fun way to do it. I'm sure it's been done before, and I'm sure there might be a more accurate way. I'm just marking a couple parts here because they're not stored in my parts rack. They're either a weird size or a weird power or weird values, so we'll have to get back to those. Okay. Let's do some caps, shall we? Alright, so we got 4 decades of caps in this tray. Let's ask for a 10 nano. 10 nano. 100 nano would be 0.1 mic, correct? 0.01, I mean. So this would be 1 nano. This would be 10 nano. Yes. I wish I would be more consistent. Yeah, so we need just 1 of these. We'll grab a couple values while we're here. 4700 puff. Oh boy, only have 2 of these. Alright, I'll get that populated because I don't want to forget which one's which. 4700 puff is C105. If we put the wrong feedback capacitor, I don't know if that's the feed forward or hanging off the compensation pin, but either way I want it to be the right value. Alright, the other one we're going to is C103. C103. Oh, you know what? Those might both be compensation components. Yeah. Yep. Yeah. So if there's one thing that I've gathered from the metrics, it's that you guys are really, really into custom transformers. So hopefully we have can take a moment to clip on the leads and really measure how this transformer is doing. It'll be an interesting test because I designed it pretty carefully, but I didn't wind it very carefully. I was kind of in a hurry. So I'll be curious to see how close our turns ratio of 1:1 came out, and that'll also expose how critical that is to function of this converter, how much margin we have baked in. So hopefully we've got enough. 2.2 mic, 0805. Alright, 7 of these. One, 2, 3, 4, 5, 6, 7. Let's go. I think these are the only 05s in the whole design. Makes it really easy to find where they're supposed to go. This is a great example of one thing that I've noticed with the T12 is it does a much better job of than my old iron when it comes to handling these giant plane shapes. A much better job. But I've seen better. I've seen quite a bit better. I just don't know. I don't know how I feel about it. Not yet. C101? Yep. Alright, so well, we'll just start throwing parts down. If we put down 7 parts, we know we got them all. Ooh. Yeah, it does an excellent job with this plane shape. You gotta be careful not to use the very tippy tip, but oh boy. Our old iron would just sit on those plane shapes and not do a whole lot. We actually had to preheat the board to solder these caps onto the planes. So as far as upgrades go, there's a measurable or a noticeable performance difference. They cost about the same, actually. Just shocking. Spoiler alert, if we do end up doing a review on this thing, while I'm very happy with the performance of it, I would never ever recommend that someone buy one of these. Sounds kind of weird, but I cracked open the enclosure, just to take a look inside, and after a brief inspection, I've realized that they weren't particularly interested in regulatory compliance when they built the thing. It definitely speaks of like it could use some love. So I'm definitely going to crack open the case and modify it to bring it closer to compliance with safety standards, and we'll never get there wholly. We'll never be able to become completely compliant, but right now it's the basic things like there's a metal enclosure with mains in it and it's not tied to earth ground, and I'm just like, yeah, one little wire gets loose and this thing becomes an electrocution hazard. So yeah, I would rather have the case be tightly coupled to ground, so if a mains wire gets loose, it shorts and then trips your breaker. Maybe that's just me. So, with big issues like that, I couldn't recommend it. But I think there's a way that you can use the underlying design that could be safe. It's the way that they've implemented the AC to DC power supply in this soldering station that was not up to snuff. Yep. Yeah, so basically I just looked in there and made sure there were no shorts that were going to kill me, and I was like, close enough. We'll make it compliant later. It's not a fire hazard. It did have proper fusing. It had proper fusing, so that's a step. That's a step. Alright. See the one mic and the 0.1. How many 0.1s do we got? Oh! Whoop. There's some parts. We got 3, that's for sure. Good thing I bought extra. It's raining. It's raining capacitors. There. This won't take too long to get cleaned up. I just gotta grab the funnel, and I'll just scrape them right off the ESD mat right into the tube. Whoops. See, look. No harm done. Oh, goodness. Alright. The rest of them we're just going to deem lost. I don't want to waste your time. We got most of them back. We got enough that we can finish assembling the other circuits. Okay. 0.1 mic, we need 108, 104, and 102. Oh, C108, I remember that one. We accidentally almost populated that with a resistor. I'm sure that would have been great. Hey, WTP Gaming? Yes, I did. I did. Which stream were you in our last stream? Were you here last weekend where we assembled the other 2 bucks? Or were you just here when we were doing the 5-volt buck? Let me know which stream you were on, and I can rehash what happened. A lot has happened in this circuit. 5-volt, okay. Yeah, so if I'm remembering correctly, where we left off in the 5-volt stream, what did I break? Was it the controller? I thought we got 5 volts up and running at the end of that stream. Because we had tested the ideal diode controller. We'd got this running. I swear we got... Well, I'll just tell you what happened with the bucks. So these FETs kept blowing up. Oh, you left early. You left early. So yeah, we got that working eventually, the 5-volt. And then we tried to roll it up to the 12 and the 15. And the 12 and the 15 were a little tricky. We're having an issue where the low side FET was, well, blowing up. It was violating the safe operating area for a brief moment, and it ended up repeatedly blowing up the converter. It wasn't like a one-time thing. It was whenever you dropped a load step that was too hard on the supply, it got a little grumpy. And by a little grumpy, I mean, shorted out the FET by what I presume is melting all 3 of the internal connections together, and then it would kind of back drive the controller with 24 volts, and then it was not great. There is an archive. You could always zip through the archive of the stream. I think I've been adding them to the UPS playlist. Hopefully I have. I've been meaning to make it easier to find. But yeah, you can definitely get all the details there. But basically what it turned into is I had to get a low side FET for the 15 and 12 volt. Well, definitely the 15, not sure about the 12 volt. Have to get one that has a higher peak power rating so that we don't end up blasting these parts off the board. And we did that and got it assembled, and everything seems to work, which is great because we need all 3 of these power supplies to function to power the Flyback. So it's very good that I got it working. Otherwise, today's stream would be pretty boring if we just solder a bunch of parts to the board and can't turn it on. Thankfully, we've got all the power we need, so we'll be very, very able to move forward. Got a C107. Oh boy. This plane shape might be a little too much for this iron to handle. There we go. Make sure the tip's nice and tinned. Yep, this is one of those that has big, beefy thermal vias. The PID loop running in this iron is a little slow. So like, it's got the oomph. You just need to leave the iron on it long enough for the iron to realize it needs to turn on the big guns. Once it figures it out, it's fine. It's just the getting there part that's oh my goodness. Alright, we gotta preheat this. I can't stand it. So what we're doing is we're just heating up the copper planes in the board a little bit with the hot air gun, so that when we're trying to solder a little component on here, like a tiny little cap, we don't need to change the temperature so much. It makes a world of difference. And you saw how I was fighting with that coming at the iron. Bet you it'll just go. Wowza. Alright. It's soldered, but it's not pretty. Let's make it pretty. There we go. Part is on the board. Hopefully we didn't crack the capacitor anyways from Sunday. Alright, sweet. So that is all the commodity R's and C's. On to the special parts. I've got a good number of them pre-sorted here. Let me know if you have more questions about that switcher. Q19. Yep, we're using the same FET. Hopefully we don't violate the safe operating area of this in this design as well. Because we ordered 26 FETs. We've got 3 now. Plus a little bit from a reorder. But, you know. Certainly not as many as we had started with. And what we've learned is for these particular parts, it's very important to get the solder on the pads, because this chip is not a huge fan of letting solder flow. Cool. So we'll do a little bit of that, get a little bit of paste flux on there. Sweet. Let's see if I can get a close-up of this, of the reflow process. Oh, that's a little closer than I was hoping for. Can I dial that back any? No, of course not. Holy cow, that is really zoomed in. Sorry guys, I'm gonna have to take this slightly out of focus in order to even capture it. Oh, that doesn't feel good. But hey, at least you can see it. Never thought I'd want a microscope that can zoom out more. Usually I want to zoom in more. Might be able to use the other camera. Actually, let me try that. Whoa. Sorry about that. Wow. Oh, yes. What's this? New camera. Never mind those scan lines. Yep. This is our new camera, primarily for looking at the oscilloscope, but we'll borrow it to get a closer view of this. Yeah. Yep, just about there. Getting close enough. I'm going to bring the part kind of in. Don't want to thermal shock it. Want to make sure they're both about the same temperature. Get the flux in there. This should reflow real quick. Boom. So now that gave us an excellent solder joint. Absolutely excellent thermal oh goodness, that was still molten. Whoa. One moment. I just knocked it off the pad. That's nuts. That was molten for a long time. But it did flow very well. Alright. And now I'm going to leave it. I'm not going to sneeze or breathe or touch it. It's just going to be fine. It's just going to chill. That's going to be okay. Yep. Maybe we'll... Here. Alright. Should be good now. Yep. So, a big thing with those bucks that was causing the failure is that we're doing current sensing with the low side RDS on. Oh, that's so cool. The thermal isolation between the floating, which it's not, there's a route, it's loud. Okay, I'm just nerding out a little. Like, it's really hot here, but it cools down right here. It's very close. Because obviously it can't conduct straight through. Anyways, the low side FET RDS on sensing is a bit of a problem. And the reason why is because RDS on changes dramatically with temperature. Dramatically. Like in these particular parts, it's a factor of 2.5 from room temperature up to the maximum junction temperature. So if you tune your current limit for that maximum resistance, when it's at its minimum resistance, your current limit is huge. It's absolutely massive. So yep, we had to play with that, get it tuned. The peak current limit's around 10 amps or so, and then find a FET that could handle that. Okay, we do not need that PTC. We need differenter PTCs. Do we need a green LED? What color do we need? We need a... Yep, we need a green, a D30. Green, D30. So yeah, I love low side FET current sensing because it is super efficient. You don't have to add a current shunt resistor that's burning power. You're only burning the power you need to, which is pretty cool. But the consequence of having a highly variable current limit, it's also a pretty severe consequence. D just requires some thinking, that's all. D30. Okay. So there's a little diode on the, or a little triangle on the bottom of these parts that tells you which side's the cathode. Just making sure to line that up with the silkscreen polarity marker. Not too big of a deal. Just gotta be a little careful to not put too much heat into these. They can get a little grumpy if you get them too hot. Oh my goodness. My hot air gun cable is getting all up in my business. There we go. There we go. Got that out of the way. Cool. Thanks for bearing with me. Thanks for bearing with me. Alright, now we got a couple red LEDs. D32, 31. Yep. Let's find these guys. Where are we going? 31, 32. Great. These are indicator LEDs for power being present on the outputs. Yeah. This was a really fun design to do. I had a ton of fun making this flyback converter, which I'll have to scour the archive. I'm pretty sure we made a dedicated video on this a long time ago. In fact, that might have been a two-parter. So I think I designed it, and I wasn't very happy with it. So I came back and redesigned it. Yeah, I'm pretty sure we've talked about this one before. I'm pretty sure we've talked about this converter before. But it's just so cool. It's so fun to do something that you wouldn't normally do. And just have a little bit of fun. It's like the artful kind of electronics. I don't think we need any of the 6-volt TVSs. Nope. Oh, do we have any of these comparators? Mic 7221s? Nope, we've got just about everything else under the sun, but no comparators. And no blue LEDs. The 1N. I think we've got a few of these. Yep, D50. D50. And we might have a couple of these. Manufacturer part number ends in 1241. 1241. Nope, not one. Cool. So we're just getting D50 populated. This one's got a little more unique polarity marker. It's got the most subtle little laser etched line on one side. Yeah, it's pretty neat. Pretty neat. Alright, so those are all the parts that I had prepped. I gotta grab my bag. It'll just take a second. We've got our big box of parts. Boom! Isn't that a big box of parts if you ever saw one? We've also got a couple other little parts bags I gotta sort through here. No, we don't need this, don't need this. No, not today. Ooh, fuses. I believe we need a couple of these. Okay, so we've got AF2C. Oh, they're both AF2C. What do we got? We got a 3.5 and a 200. Which one of these do we need? We need the 3-5. We need that fuse. Great. Not quite sure where to put this giant box of parts. I'll just put it in my lap for now. Hey, hey. Welcome to those watching. I think we got a couple more that joined, so welcome to the stream. Okay. Interesting. They have a ESD bag that they put these parts in, but they didn't tape it. But then they put it in like a moisture sealed bag. That's pretty bizarre. Yeah, DigiKey's packaging approach is more of like the shotgun method, where they just put everything in a static safe bag. I'm like, yeah, that'll work. That'll get it done. It just, you know, seems kind of excessive when you get 1,000 static safe bags. All right, got fuse clip. So we need 120 ohm ferrite beads. We need our 0.1 ohm shunt. Yep, 100 milliohm. 0.1 ohm. Then on the caps, we need the 22 mic. I believe there's one more resistor in here. Yes. The 1 ohm. So we got the 1 ohm, 100 milliohm, and we need the 10 ohm. Uh-oh. Did I miss one? Uh-oh. We got the 1 ohm, 100 milliohm. We need the 10 ohm. Interesting. I'm sure it's in here somewhere. Ferrite bead we need is the 121, alright. $60 ohm ferrite bead, 10 microfarad, 2.2 microfarad, 470 pico. Oh, it's actually not in this stack. Interesting. Interesting. I might need to go hunting. Might have fallen out of my stack. That's no good. Hmm. 12 amp. Schottky. Okay, so we need the NPN 600 volt Schottky. I believe that's the one. 600 volts SPC. Yep. Then we need a 27 volt Zener. Indeed. We need our PNP transistor. Do we need our PFET? No. 18 volt Zener. I believe we need that as well. And we should have an 8.2 volt Zener. We don't need the 24 volt here, do we? Oh, wow. Yeah, we do. All the Zeners. Okay. That's a lot of diodes. Maybe I should think about consolidating a couple of those parts, eh? That seems a little excessive. So that 10 ohm part, I don't know where that is. Wait, we need a 2512 1 ohm. Uh-oh. That part didn't seem big enough. Oh. Oh, there they are. Thank goodness. Okay. Sweet. That'll get us going for a little while. We'll have to dig one more time for parts, but that'll be the most fun. Okay. Back to business. Let's get our fuse soldered in. Here she is. Yep, these are all PTC resettable. I'm trying to do an excellent job of leveraging fusing in this design. That was one of the big things we got wrong on the Gen 1 UPS. The fusing strategy was a little lackluster. Even once we got most of the technical stuff hammered out. Yeah, just like, it's the little things, you know? Oh, goodness. Come on. You know you want to. Apparently it doesn't. Alright, reflow time. Get some flux in there. We'll get this part on. We'll get this part on the board. Oh my goodness. Gotta be careful with fuses. Especially resettable ones like this. If you abuse them, their current limit becomes less and less accurate. They just start tripping at obscenely low currents, and it's like, why? Stop. Cool. Alright. On the board. Got a couple ferrite beads. Get these where they belong. Welcome, welcome. Got a couple folks joining. Depending on what those 10 ohm resistors are, we can probably sub in a short-term alternate. I'll have to take a look if we really can't find them. I have every intention of running this design through its paces today, so we will make that happen. Yeah. It's gonna be a lot of fun. There's just something about 5 kilovolt isolation, like meeting big routed slots. It's just exciting. You know? It's just exciting. Maybe exhilarating is a better word. Oh yeah, so I did a little isolation test, right? A critical part of any isolation boundary for a switch mode power supply like this is the transformer. That's the primary leakage path, especially for something like this where we're using a custom transformer. You know, everything comes with a rating, everything comes with a data sheet. You're just kind of like, alright, this one's rated for 5 kV at 60 hertz and some leakage current, and that's acceptable to me, so I'm going to move forward. Something like that. Well, you can't look at the datasheet when you made the part. So I had to do some testing. I made a preliminary version of this just to make sure that it kind of worked before I went and made one for real. Yep, it was shocking. No, I'm kidding. Oh, that was terrible. It was very interesting, though, to see what we were able to do. I was able to achieve 5 kV DC isolation. When I switched it over to AC, it skirted right around, and I think it arced out internally. I haven't actually done a teardown of that old transformer, but I need to see exactly where the isolation broke down, based on the fact that I couldn't see. One moment. This is the. Do I even need this? Why did I just unpack this diode? I don't think I need this. 12 amp, 100 volt. What? I was getting distracted. No, I don't need this at all. FSV 121. No, this is for a different supply. It's for a different time, a different day. 1 ohm, 2512. How many of these do we need? 1 ohm, 2512. 4 of them. Holy cow. Oh, these are part of the Zeners. Yep. So these are performing 2 critical roles for us. 2 of them are snubbing. Actually, one of these should be no pop, I think. Oh, we'll figure that out. Oh wait, 4, not 2. Yep, so 2 of them are handling the flyback snubbing. The other 2 are part of the shunt of the Zeners to take some of the brunt, so that the Zener diodes aren't dissipating the full extra power. Yep. These are beefy resistors, though. Good thing, because they're in our design to take a lot of power. Yes. Ooh, that cold plane though. What does it say? It says we're only at 17% power. That's what I hate about this Iron Man. It's only giving me 17% of the peak power. But I'm sitting here waiting for it to heat up. Give me 100%. Give me all you got. I want to sit here waiting around at 17% power. Maybe I can tweak the PID parameters. Maybe they have a training, like a 3D printer has a trainer to tune the PID loop, where it kind of recursively heats and cools and figures out what's going on. We should do that. We should get an auto tuner on this to okay. Yes. All right. I'm gonna double check those, just make sure I got good continuity, because if these don't, that is going to be a huge issue for this design. They basically prevent the flyback from, alright, there we go, 1 ohm. Cool, yep, looks like that worked a treat. 22 mic, 25 volts. 2 of them, C110, C109. Ha! These are some big caps. And what do we got here? The 0.1 ohm. I believe we just got one of these. R127. Yes, it is our current shunt resistor. Gotta be able to measure those peak currents. Gotta be able to prevent violating the safe operating area of our FET. Wouldn't want a repeat of our buck converters now, would we? No, no. All right. All right. You know what? I'm feeling it. You know what I'm feeling? I'm feeling a close-up for this next capacitor. Let's do it. It's been a while since we did a close-up view. There we are. So here's our work in progress. Here's where we're going. I'll get you a more isometric view. There. That should be awesome. It's going to come in here and heat up the solder. Got our component staged. Gonna get it in there. This is a big part. Takes a little while to heat up. Alright, we've got it tacked in place. Now we come in with our solder. Need to get this other side of the component solder down. So you touch the component and the pad and you just feed some solder in there. Again, this is a big part. Takes a fair amount of solder. And we'll just scoot down to our friend C110. Same dance. Now you gotta be especially careful with these big caps, because they can crack if you get them differentially heated. Those look okay, but if we find a short, we'll know why. Oh, did you see me look over? Yeah. Well, I'm just trying to pay attention to you guys, trying to be attentive. Appreciate you hanging out with us, WTP Gaming. I appreciate it. You've been sticking with us through a lot of SMT assembly. I really wanted to get a little more prep on this, but that's okay. That's okay. I think we're making the most of it. Hanging out, having a good time. I mean, at least I'm having a good time. I've got coffee. 24 volt Zener. 2 of them, 56, 57. D56 and 57. Okay, so these, back at the start of the stream, I was talking about how there's a couple Zener shunts that, sorry, bag noise, I won't try to talk over it. How there were a couple Zeners that do a lot of the clamping. That's these two. So these two Zeners, basically if we get over 24 volts, they just start dumping energy. So they'll start, basically any current that the load doesn't need, they'll take it. They just take that current and eat it up to bring the voltage back down to around 24 volts. In a normal situation, those parts never do a thing. They never do a thing. But they're absolutely critical when we're risking damaging a part. Like we could be blowing up a couple linear regulators and then all that downstream circuitry. If this regulator gets out of hand, speaking of this regulator getting out of hand, I better make sure I put these diodes on the right way. Seeing a polarity marking. That would lead me to believe the negative sides are aligned correctly. Get this in diode check mode. And I will come around here and we should see around 0.7 volts. Yep. Good. They usually make these things intuitively obvious because they want you to put the parts on the right way. And there's just industry norms, but I like to double check when it's the first time. It's been a while since I looked at this component data sheet. And if we put these parts on backwards, we are forward biasing a diode through a 1 ohm resistor to ground, which with the fuse and everything else, I mean, I guess that would be fine. Ooh, that is not great. These thermal reliefs, not super. Not super. Hider, solder. That should be sufficient. There we are. That was D56, D57, 8.2 volt Zener. So now this is getting into that fun feedback network. .2 volt Zener, D48. Oh, went through our isolation slot. See what I mean about the shotgun approach with DigiKeys packaging? There's just so many bags. What am I supposed to do with that? Alright. I said D48, right? Yup. 8.2 volts. Now these are all marked the same way. These are all in the same product family, so once you figure out one, you got them all. Whoa, our current shunt resistor was never soldered in place. What? Why didn't you tell me that? I'm just kidding. I'm just kidding. Oh, I'm sure somebody was screaming at their monitor like, "You forgot to solder the pin!" I don't even know. Can you guys see that? Can you see the board in that detail? Should I zoom in? Do you want me to zoom in? I can zoom in a little more with that camera. We have the technology. So let me know. I don't want to get too close. I want you to be able to kind of see what's going on. So and we got the 18-volt Zener. Yeah, so this is the critical way that this circuit works. Zoom it. We want more zoom. Consider it done. Let me make sure I didn't throw that out of focus. I can also do the ultra mega zoom. If I need to zoom more, I can. I just need to adjust the camera a little bit. So hopefully that's good. Thanks for letting us know what you do. Timothy, hopefully Tim's okay. Kind of want to call you Tim, don't know why, but hey, welcome to the stream. I appreciate you. Oh, by the way, I think we got a couple new viewers today. I think we do, but if you're a fan of EEforEveryone, we've been loving on the community a little bit. We're doing a sticker giveaway. There's a link in the description if you want your very own uniquely serialized thank you note. That one had a little bit of flux on it. Don't worry about that. If you want your own sticker, uniquely serialized EEforEveryone, there's a survey link down there. It's a sign up. It's closing pretty soon, so if you want to grab your EEforEveryone sticker, it doesn't cost anything. Just want to say thanks for all your guys' support. Okay, this should be D49, 18-volt Zener. Yep. Yes. Oh man, we're getting close to the end. I'm just like tingling with anticipation. I'm so excited to power this on and see what happens. I mean, I know exactly what will happen. No, I'm really excited to power this on and see what happens. Okay, we got a PNP 3906s. Now this will be tricky because we've got two parts that look exactly the same. So I got to be pretty careful with ref des on this one. Okay, so we did the 18-volt Zener, we did the 8.2-volt Zener, we did that guy. We're missing D53, I think? Yeah. And D54? D52, what the heck? Oh, those are on that side. Okay, need to find those yet. D55. Alright, so we got a couple more there, but somehow I jumped onto transistors. Whatever. 3906, Q17, Q18. We'll get these on here. Yeah, see, I went and I made it nice and easy for myself by populating all these little passives around it. Well, you just scroll past most of it. I can make it shorter for you, WTP. See, here's the problem with trying to give stuff away. It's super hard to give stuff away because it's really easy to break the law when you want to give stuff away. So you gotta give like a terms of service and everything else. It's really just like your name and like your address. It's really all we need. You just gotta like scroll past all that garbage on the first page, click I agree, and the rest is easy. The rest, I mean, read it carefully like everyone else. Yeah, it is a little funny, but that took more time than I care to admit to get together. But, you know, it was worth it, I think. I think it was worth it. Yeah. Yeah, I'd rather give you a really long thing to scroll past than like 100-page essay. None of that. All right. 3906. 3906. Okay. So, naturally, one of these ICs pins is going to a giant thermal plane. So we'll have to get out the hot air gun and get in preheat. I was trying to tin the pad. Just tin the pad. I couldn't do it. Gotta do some gymnastics. By the way, guys, let me know if you want me to zoom in a little more. I can. It'll just slow me down, so unless you want me to, I'm gonna keep trucking. Alright. Okay, now I gotta preheat. Yep, there is nothing. Oh! Yes! Great question! Yeah. So, there's a couple fun parts of this UPS coming up. This is testing two things. So these are press fit terminals. And the reason why I wanted to use them on our proto board is because I wanted to make sure that my footprint got the hole size right. Because if the hole size isn't perfect, you try to press fit the component and it either just falls right out because, you know, the hole's too big, or the hole's so small that you like crack the board when you get the part in there. Both of which, not really ideal. And so I was like, hey, I need a terminal. I want to test this 20 amp current measurement circuit. Sure, this press fit thing's rated for 100 amps, and we don't really need 100 amps. But I figured we'd just give it a shot. So that's testing the new isolated current sense IC. So that's a 5 kilovolt galvanically isolated Hall effect current shunt or current sense IC. And then we've just got it hooked up to a couple 5M terminals. So yeah, literally all this is we feed it power, and then the IC does all the heavy lifting. It does all the work. Just feed it current through and see what you see. I'm making sure that our assumption is right for what's coming out of that signal, because I believe it's made to hook up to a 5 volt micro and we need to translate it for a 3.3 volt micro. There's an offset and then your measurement, and so like a strict amplification won't quite fix it. Won't quite get you where you need to go. Hopefully that transistor still works, because I feel like I just cooked the crap out of it. Good question. Good question. Great question, actually. Yeah, there are a lot of fun circuits on here. So we've got an analog sense, an analog voltage sense, got a analog current sense, we've got some transceivers, we got a 4S lead acid battery charger, a 2-stage charger, we've got a third redundant power supply, so we got two 24 volt inputs here, but there's a battery backup to 24 volt converter as well. Man, this is a fun little prototype. Fun little prototype. All right, 27 volt. Which ones? I assume it's these two, 52 and 54. 27 volt Zener. Yep, that looks right. Yeah, hopefully that answered your question. WTP, let me know. Let me know if it didn't. I'll try harder. I think that answered your question. It's pretty much just a, that looks neat. What's up with that? Yep, that's coming up in an upcoming stream. I think we're doing, on the agenda, I think we've got some of the battery charge related circuits next. Then we're doing some of these little 5-volt based ones up on the top. We're getting to the current measurement one soon though. I think it's within the next month. It'll be coming up on a Saturday stream. Hopefully when I've been scheduling these, it's been letting you know. So I've been dropping the estimated date on YouTube, I mean, at least a couple days in advance, so it like does a countdown. Hopefully that's helpful for you. I try to not spring these on you, so if you want to call in, you actually can. D55. We're gonna need to trace down D53. I know that I've seen that diode around here somewhere. Can't remember where. Knowing my luck, it'll be in that giant pile of parts on the floor. Okay. So we're gonna kind of do this the same way that we were doing the rest of those. Gonna tin this on the back just a little bit. By the way, this is super not the right way to do it. If I were doing this right, I'd be using paste and we'd just reflow it. It'd be excellent. But instead I'm doing this. It'll be alright. It'll get the part on the board. Sure, maybe it only lasts 2 years instead of 20, but whatevs. And now we melt. Hey, this secondary side's looking pretty done. That's pretty exciting. Couple more NPN transistors and we'll be done. Yeah, I'm gonna make it my life goal to get all the boring parts on before we start the stream next week. Life goal. We'll see if it happens. We'll see if it happens. I just think it'll make it a little more fun. While that cools down, we'll get these NPNs. 3 of them. But yeah. While we're here, we got a little bit of time. So I've been playing with the idea of a couple short series that we might want to do either towards the end of the UPS project or before the end of the UPS project. So there's 2 things that's come up. One of them's a brushless DC motor driver, like building that, and my idea would be to build that as like a shield for an Arduino, because you can get like STM series dev kits. You can get like a 32-bit micro from ST that's compatible with that kit. Wow, the irony of having an ESD mat and dropping these transistors onto a sheet of paper. The irony is not lost on me. I should really do a better job of using the ESD mat that I set up. Anyways, doing a motor driver that could drop onto like an STM32 kit or a Cypress kit, because they've got some of those that have an Arduino compatible header. just basically a general purpose board that gives you all the analog and digital that you need to do censored or sensorless control of brushless DC motors. I was like, man, that sounds like a really fun kit that we could put together for you guys and let you play around with some motors at home, because I mean, some of those exist, but they're like at a lower power level or a lower voltage level, or they can't do field-oriented control, which is another word for sensorless control. So it's like we could just shatter some of those limitations. And then I was thinking, I've heard of this website called Tindy, so I might even be able to kit those up and sell that as like a kit that you guys could build at home. I have no idea how much it would cost, no idea what it would be, but it just sounds kind of fun. It sounds like a lot of fun to make a proper EEforEveryone kit. And if you guys are into it, I can be into that. The other thing that I've been thinking about making into a kit would be a DC electronic load, because those get pretty spendy, and there are some that are available like for pretty cheap on Amazon or whatever, but those have a reputation for occasionally failing short and blowing up whatever they're connected to, so we would make one that doesn't do that. Yep, so that's pretty much the whole idea. A better one of those. D53 is the only one that's missing right now. So we got D55 on the board. That is all of our diodes. Excellent. Obviously, except for the missing one. Okay, I'm gonna do a quick look through these bags, the ones that we've already rejected. Looking for the on semiconductor diode. I'm pretty sure it's in this pile. Fuse, GM control. I'm pretty sure there's one of these in the box. Cleaner. PNP. These are the diodes that we didn't need. S2 micro, not these. Where did those go? They were right here. Okay, I stand corrected. They're not in this pile. Perhaps they got miscategorized as an IC. Maybe they'll turn up. Yeah, they're super not in those bags. That is a little concerning. Oh, wait a minute. What is this? Could it be? NV? No. Oh, that looks right. NVRT 260. Yes, there it is. Excellent. $3904, $3906. Electronic load. WTP gaming. But I like explosions. Great point. We'll make an explodey electronic load. Now, okay, I'll keep that in mind. Electronic load is the preference. If we move forward with that, I will definitely make sure that we do the electronic load. Ferrite bead. Ferrite bead. I'm glad that you remembered the point. I never actually asked the question. I'm really glad that you kept me honest. Temperature sensor, like that. 52 kilohertz. UC 20. Nope. Switching voltage regulator, LT 30. Yep, that's the one. None of that. None of that. We need a couple more of these though. We need a couple LDOs. 3.3. Wait, that's not right. We don't need a 3.3 volt regulator. We need a 5 and a 15. Voltage reference. Flyback controller. Wait, what? $3,800 EFE. We need the 3803. Ooh, that would have been interesting. I almost put the wrong switch mode power supply controller on the board. Wouldn't that have been exciting? More low power stuff. Oh man, you're killing me. You're killing me. Optocoupler. We need that. 1.5 amp. Gate driver. We need that. 15 volt. Linear regulator. We need that. Okay. Let's make sure I didn't miss this. So I think we're looking for a 7805 and a 7815. Yeah. I think I've got some spare 7805s laying around. If we can't find that one. That is bizarre. There it is. There's a 7805. Cool. I was gonna say, I pride myself in having the parts to complete the build. I prefer it when we have them all. Yep, because these go in their respective location. Yes, we did the 100 milliohm resistor. We did the 1 ohm resistors. We just need the 10 ohm 125, 124, which are the gate drive resistors. So I'm just going to populate a 5. Wait a minute. If we had a 5R11, bet you the other one's right with it. Oh, whatever. 15 volt linear regulator. $78.15. Got ourselves a MOSFET driver. These are all pretty great. They've only got one place to go. There's only one place that fits them. C28. It is pretty nuts how small things like this gate driver have become. Like, the fact that that little part can sync and source a full amp. That is just awesome. Excellent packaging. Excellent packaging. Optocoupler. Here's our diode. Okay, let's get these parts on the board, shall we? Alright, gonna do a diode check. polarity on the flyback. Diode, excellent. Welcome, welcome. Got a couple more people in the stream. It's a pleasure to have you. You picked a great time to join. We are just about done with this assembly. We've got a super fun suite of tests to run through. I am pumped. We're testing out our own, we'll say custom, but we won't say kludget, we'll say custom. Got a super custom method of controlling this power supply that involves Zener diodes, optocouplers, and oh, you know it's going to be fun. Oh, you know it's going to be fun. Alright, let's make sure. This is another one of those where if the diode's not connected right, we're going to blow up the FET. So let's just make sure. Yep. So we're getting good connection. Good connection on that diode. Alright. Wow. I have no idea which pin is pin 1. Like, it's not, the symbol's symmetrical. I bet you I made this footprint, because no ordinary idiot would make a symbol like that on the silk screen. Note to self, fix silk screen. Alright, so we can figure this out just by using the diode check mode, because I know that we're driving the diodes on this side and it's got the open collector outputs on the other side. So I'm going to quickly check, make sure the diode is forward biased in the direction that we would expect. This is a 3906 transistor, so we expect that we're switching the hot side. And so if I measure the diode drop from there to there, oh, there it is. There's a volt. There's a volt. There's a 1.6, which is more of what I would expect from the diode in here. Oh no. Alright, I'm gonna grab this schematic. That part is just a little bit too important to throw it on willy-nilly. More bucks, come on. Where's the fun one? Here it is. Hopefully that's reasonably in focus for you. Feedback. Pin 1 to pin 2 is a forward bias diode. Pin 1 should be pulled up with a resistor. Pin 2 is being pulled to ground. Whoa, wait, what? Q15 should be the 3900. Did I populate those wrong? Oh no. Q14 should be a 3904. Let's check. Q14. So pin 1 to pin 2. Did I get that backwards? Pin 1 to pin 2 is a forward bias diode. R105 goes to ground. Nope. I think I put a 3906 there. And Q15 Yep, so that's gonna bias R107 to ground. Oh, wait a minute, no, Q15's right. R107 goes to ground. I think I did that right. At least that diode's measuring right. Such that we'll turn it on, and if this is ground, and we're switching ground, then that would tell me that is correct. Okay, so this might work. I think I did it right. I really need to add a pin 1 indicator. Really need to add a pin 1 indicator. My word, that was stressful. This is kind of the same deal as all the other surface mount parts. It's nothing too special. Just so happens this one's across a major isolation boundary, but that doesn't change the method of assembly. It just means we're doing it over a slot. Yeah. Mm-hmm. All right. 15-volt regulator. I believe that's U30. U30 15-volt regulator. Getting it done. Okay. So I'm going to just put a dab of flux on the back of this part. We're going to see if we can do this without tinning the part explicitly, but just making sure it's got plenty of flux. That's the main issue with tinning parts like this. There is flux built into solder. So if you try to solder without flux, it doesn't flow very well, reduces the surface tension, makes it stick better, does all sorts of good stuff for you. And then through adding the solder directly to the board, there's obviously no flux left. It all like burns off before you get the part in there. But now we're applying the flux directly where we need it, right on the back of that part. Heat it up, reflow it. Oh, we'll be good to go. We'll be good to go. Yep, that's flowing great. Just had to check, just had to check. Alright. I should really do that other LDO while I got it here and it's already hot. Which reminds me, we had a gate driver that we pulled out and set on the board somewhere. Where did that go? Did it fall through the board? Yeah, there it is. Alright, 7805. You are next. Yep, so that's the principle. Basically, loose current regulation, or loose voltage regulation through the flyback, and then we get our tight regulation from these LDOs. Should work pretty great. Should work pretty great. Let's see if I can do two things at once. Well, looks promising so far. Alright, alright. Get this going. Yes. Alright, solder's melted, the part's just not very well aligned. Oh, seized up. Got a little cold on us. Alright. But all shall suffer. Well, we've got the iron hot. Everything's ready to go. See if I can't get the gate driver installed before I forget about it and knock it off the board again. So in this case, there's an option. We've got pads on the board to do asymmetrical gate drive. Challenge for the digital load. Make it as small as you can, possibly stacked boards. Yeah, it's all about power level. I need to figure out what makes sense for power level. But we will definitely make it as small as we can. Yeah. I don't know if this would be something where I'd want to make it compatible with dev kits. So like, I'm thinking we'd probably make a default firmware image so folks could get this thing going. But see, the funny thing about as small as possible for DC electronic load means that it's also going to be low power, because usually you've got some kind of, you need to put the power somewhere. You've got to dissipate it. So if it's really, really small, you either need a really annoying fan or just got to make it really low power. Neither of those sound particularly fun. I like high power. But for whatever power level we design for, I will certainly make it as small as we can. There's just practical limits. There's practical limits. Oh my goodness, I have a terrible solder bridge on this part. Then we've got some trusty solder braid. Alright, there we go. Alright, that should be good, assuming it still works. Yeah. The electronic load gets me pretty excited though. Just the idea of it, because it's, yeah, you can get a very precise electronic load that will cost $200, $300, $400. But for what I'm doing, like, we're using resistors to replace it. So it's like if you need a stopgap, you know, like 5% accurate. I feel like we could save a lot of money by sacrificing a little bit of precision. Yeah, I like that idea though. I'm glad that you're dreaming. I'm glad that you're excited about it, thinking about it. We will certainly share the progress so we can shape it as a community. Yeah, close up. No problem, JD. Boom. I missed. I guess not. Yeah, so there's E28. This is viewing it from the back, so this is a SOT 25. It's a lot like a SOT 23, but it's got 2 extra pads over here. Those are the 2 that weren't shorted. These are the 3 that we did short and then use the solder braid on. You can see there's it's a little anemic. Alright, I can't leave it. I can't show you the close-up, show you it looks terrible and not fix it. I'll fix it. I'll fix it. Welcome, JD, though. Pleasure to have you. Alright. So in this case, we got a little solder bridge. No problemo. This will be a great opportunity to show you the power of my good friend Flux. This is something where we've got a little solder bridge, but it's not due to an excessive amount of solder. It's just due to a lack of flux. Boom. A little bit of flux, a little bit of heat. Good to go. Hopefully that satisfies you. We can do a close-up of U26 as well. It's a very similar component. This is the controller that we need to use. And show it in progress. Hopefully I can do this one better. Ooh, my tweezers are sticky from that last part. Alright, so here's the component. I'm showing you both to show you, and so I can figure out which one's pin 1. I think did I actually? No way. No, it's upside down. I was gonna say, did I get that randomly right? So you should see the arrow up on the long side now. There it is. Pin 1 on pin 1. Excellent. Coming in with a freshly tinned tip. Oh boy. That bodes well. That bodes well. Alright, here we go. We got it to flow. This is a pretty small part. It will not take much solder to get this on the board. Okay, there we go. Now I've got it tacked in place. I'm going to leverage a technique where you just kind of lay the solder across. Oh goodness. Oh goodness. Remember what I just said? I can solder any pin except for that one. What do? Solder that pin. Alright, way too much solder on this part. We'll see if I can get the flux to make it obey. I think there might be too much. I think I might need to come with the solder braid. Yeah, there's too much. There's just too much. Yeah, alright. My bad. When you have lots and lots and lots of pins, it's a little easier. You've only got 6. You don't have many pins to like distribute your flux over or distribute the solder over. Oh my goodness. If this controller lives through this abuse, I will be shocked. Like in a good way, but still. This is some pretty serious abuse. Oh my goodness. The short still lives on. What the heck? Okay, one side's looking excellent. Oh, yes. Got it. Crushed it. Oh, thank goodness. Now here you guys are gonna start thinking I didn't know how to solder. Joking. Joking. That's tricky, man, these tiny little parts. You don't do that every day. Don't do that every day. Whew. Well, saved the hardest ones for last. I think that's through it though. So we got our gate driver, we got the 2 LDOs on the board, got the diode, got the opto isolator, we got the controller, absolutely. We got the transformer that we need to install. That one's custom mount, that one will be last. We got a switch, some test points. Right, that resistor we need a gate drive resistor. 10 ohm. Ha! Found it. It was right with the 5.1 ohm. Funny that works. 2 of these, one of them will do something, but I'll just put them both on the board anyways. What size braid is that? JD looks great. Man, I appreciate you. I wasn't feeling too good about that solder joint. I appreciate that you think it looks great. And that makes my day. The solder braid. What do we got here? We've got a no clean wick 2.5 millimeter width. 2.5 millimeter width, no clean. Yeah. Cool. A couple gate drive. R125, R124. Yeah, I am super pumped. I've said it a couple times before, but I think a couple people dropped in later. I'm super excited to test this one out because the control mechanism, if you've been watching the series, it's a little novel. Like, there is a chance that this thing will be wildly unstable. There's a chance this thing will boot up and just blow up. There's a chance it'll never turn on and it'll just blow up. Yeah, took a minute, but you got it. Yeah, you could even say it took a hot minute. Yeah? Will you let me get away with that? Will you let me get away with that? That kind of dad joke? Can I pull that? I'm not getting scolded in the comments yet. I think I can get away with that. Yeah, took a hot minute. You guys are the best. You guys are the best. Alright. Oh my goodness. Okay, what do we got left? We got a couple caps, we got test points, and we got a transformer. Everything else is on the board. That diode is a no pop. Oh boy. Oh boy, we're done. Oh yes! Last time I was this excited on the... Was that like an in your head? You were like, yes! Hot minute. That's good. That's good. Yeah. Last time I was this excited was right after we figured out how to fix the buck. Oh! Hey, JD, were you on the stream when I was talking about the how we fixed the 3 bucks? They all work now. I got them all fixed. Were you here when we were talking about that? Okay, so I'm gonna put test point on there. That's on the input side of the ferrite bead, so we can take a look at the ripple at the input. Okay, cool. Yeah, so basically we left it off. We thought it was the peak current limit. It was. True story. I think we might need to jumper in the gate drive. For some reason, I have a feeling that those are not connected. Yeah, so what I did is I tweaked the programming resistors on the current limit, and I had to put a beefier FET to handle the peak power. It was violating the safe operating area of the part. I can't remember if that video went live or not, but we've got a video talking about it in pretty good detail. So definitely keep an eye out for that. Super neat. Just got it trimmed up because we need all 3 of these supplies to make it work. Oh, these are connected somehow. What? How is that 15 volt input connected? There's like no trace running to that. This is a 2-layer board. What? And yet, It insists. Does it like snake around all over? Really? That's connected? It's connected. The 24 volt input too? Ah, the 24 volt input's not connected. The 5 volt is? Yeah, okay. So we need a jumper for the 24 volt input, so I guess we'll put a jumper on that as well, since we need to get an alligator clip over there. And power ok's got an LED. Shouldn't need that. Stop, we've got a switch for, shouldn't need that, so we'll just need our isolated output. We need 15.5 and the isolated reference. Because of course, ground does not apply for this converter. This couldn't care less about your ground potential. It's about 5 kilovolts away from caring about ground potential, which I hope we never find the limit of. Alright. Gate drive resistors on. Tacked in place. Yeah, and you were probably also here when we were talking about the solder station. You might notice the soldering iron looks a little different. Definitely bought. Yeah, 5 kV DC. I technically didn't test this this transformer, so I just used a better construction method. So I'm assuming that it's as good or better. Basically, in the first one that I wound, I just kind of wung it. Just tried to get the spacing right. But they kind of have a mind of their own. The wires, when you put like 40 windings, there's 40 turns in that tiny little transformer. That's actually why I wound it not on the stream with you guys, because it's like, I like you. I don't want to make you watch me wind 40 turns on this tiny little bobbin. It's just tedious and takes forever. So I was like, maybe I'll spare you the gory details on this one. Can always make a video about it, right? It doesn't need to happen today. So yeah, so the original one here failed at 5 kV DC, so you just short the primary turns, short the secondary turns, apply the high voltage, and it arcs or it doesn't. I'm thinking what happened is it snuck around the barrier tape on the inside. I'm thinking that's how it failed. The live stream winding and whining. Yeah. Am I winding and you're whining about how long it takes, or am I just whining the whole time? I can do both. I can do either. I'm all for that. Yeah, I just wouldn't want to do it as a part of this, right? It's like we want to get to testing this thing. We don't want to have to sit here and watch me wind a transformer for an hour. Yeah, what AWG? We used this awesome Chinese grade BN Teco high quality polyurethane enameled copper wire 30 gauge. Yep. And so what we did is we put on okay, so when I said I got lazy with the winding, what I meant is I was supposed to put 42 windings exactly, and I counted and I was like, well, it's about 20 when I did one row. So what if I just do a second row on top and call that good? Yep, so that's what I did. So it's 40-ish windings on the one side. Then the other side's also got 40-ish turns. And we'll see how it goes. It's supposed to be a 1-to-1 turns ratio. 42 turns per. Yep, this thing's a flyback, so it needs a fair bit of inductance that would normally not be desired in a switch mode power supply transformer, but that's one of the reasons why flyback transformers tend to be lower power, because they actually need to store the energy going through them rather than directly pass it from input to output, so they're much, much, much easier to saturate. Wonderful. Got ourselves a switch. Turn on the supply. And we just need our big caps. What do we need? 2 of them? 2 of them. Yep. It's amazing how many turns of that tiny little wire you can fit. Okay. Hopefully I don't need to... Oops, sorry. I am doing a terrible job of framing. Thanks for being patient with me. Okay. Melt the solder. Scooch the cap on. Yeah, so handle these just like any other SMT component. They're just massive. These caps are awesome so far. I've been keeping a close tab on ripple current because they don't have the best ripple current rating. But I'll tell you what they do have. They got the best price rating. Oh, did I flip the board over? Did you see the rubber feet? Yeah, it helps with the whole through-hole stuff. Otherwise this thing would be teetering all over the place. I don't remember, I think we did that in the unboxing stream, which was otherwise fairly uneventful, but we had the awesome idea to get some rubber feet on this thing. Yeah, just keep it off the board a little bit. Like, the ESD mat isn't conductive, that's not why. Well, the top isn't conductive. There's a bottom, like, conductive rubber layer, but that's not why we did it. We did it just to make it easier to work with so it's not, like, rocking all over the place. I think we did 3. No, I did 4 feet. I did 4 feet, but... yeah. Okay. After a quick final inspection, everything looks quite good. Let's clean off this board a little bit. Let's get some of that excess flux off of there. Some of these dense regions of the board. Just makes it a little prettier to look at. A little less sticky. All around good time. Alright. Who's pumped for some testing? Who's pumped to get this thing powered on? I'm gonna be very disappointed if it blows up. I am 15 out of 10 over the moon to get this supply powered up. We've been assembling circuits, debugging stuff for, what, 3 weeks now? 3 weeks now to get ready just to power on this converter. It has been a long journey. That's what makes it fun. While we're cleaning, I'm gonna clean up these. Yeah, dude, JD, I sympathize. Alright. Good enough. We can get it perfect later when there aren't power supplies to test. Right. I specifically designated this one as the primary on a whim. solder positioned. Unfortunately, I still only have 2 hands. Still, can you believe that? Alright, tacked in place. This one might actually need a second tack. Alright. So we should have an approximately 5 kilovolt DC isolated. Maybe 5 kilovolt AC. I think I wound this one better. Maybe this one can do 5 kV AC. We're not going to test its limits today. We're not putting mains on the other side of it. But we could. Andrew, thanks for joining. Yeah. Now, if that doesn't look like a power supply, I don't know what does. Ugh. Who needs a list of parts? Get rid of this. Alright, we're going to do a quick transition here. Do a quick transition into the testing portion. Should only take a minute. We've already got camera. We'll get the scope fired up. Get this extra stuff out of here. We've got a pre-planned list of tests. I am definitely open to suggestions on what we test first. Yes, right now the plan is basically just going to get it powered up, do some line regulation tests first, and then which is the starting lead on the Flyback? Which is the starting lead on the Flyback? Starting lead on the Flyback. So it's got two windings. The inner winding is what I'm using as the primary. The external one is the secondary. They're symmetrical. It's 1-to-1 turns ratio, so we can populate it any which way. It doesn't matter for this one. Doesn't matter for this one. If it was not a 1-to-1 turn ratio, that would matter a lot more. Yes. No. Yeah. All right, you can see that. Got the probes here. Got the power supply. Can't quite reach it. How's that? That seems to work. Okay. That looks about right. Is that good to you guys? JD, I'll take that to mean I answered your question. Thanks. Yeah, no problem, man. I love answering questions. Okay, so as a small testament to the history of getting where we are, just want to show this again. This pile of parts right here, these are all the FETs and controllers that died to give us 5 volts, 15 volts, 12 volts. RIP. Just need to grab a couple of resistors here from the bin. This is a much lighter load supply, so we've got 100 ohm resistors, 27 ohm, 50 ohm. We're going to be using these today. Finish off the supply. We've also got this resistor network that we made. I believe these are 50 ohms per, so we can do a 100 ohm, 50, or 150. Ooh, 120. Alright, that's enough delaying. Who wants to see this thing on? Someone want to give me a countdown in the comments or something? Want to give me a 3, 2, 1 boom? I'll synchronize my power on with the boom as well as I can. Let me make sure we're in the valid operator. Yeah, 23 volts. We're good. We're good. Alright. I don't see anything in the comments. Oh, nice. I mean, I hit it after you guys said 1. Ah! Alright. We'll see. Let me know how I did. Let me know how I did. You, like, hesitated after 1. And I was like, I'll just do the same cadence. Ka-dunk! Hey! Oh, wait a minute. Wait a minute. Wait a minute. We forgot an important part. We forgot the jumper to bring 24 volts over here. That's kind of important. Alright. Let's try that again. Yeah, looks like it's still on. I mean, oh, we turned off the supply. Yes, of course it didn't do anything. It's off. Oh my goodness. We turned it on, and it's just on now. What is that? Did this design just work? Oh my goodness! Did we just get 5 and 15? No way! No way this just worked out of the box. Not a chance. Alright. ISO ref. Let's check ISO 15. 15 volts. Let's check ISO 5. 5 volts. I have to keep a tab on our flyback voltage. Alright, what do we got over here? We've got 17 volts. So we're regulating to 17 volts, which makes sense because I think our feedback diode is trimmed to 17 volts. Alright, so let's take a look at the schematic. Let's probe a couple critical nets. That is awesome. Tested. Hey man. Dude, you hopped on at the best time. You are not late. We just powered this thing on. I flipped the power switch. So this is the 5 kilovolt isolated flyback converter, dual output, all that nonsense. And it appears to work. First time. What? Happy you could join us, mate. I am so excited right now. The 5 and 15 volt rails just measured good. Power consumption on the whole board right now is we got 3 bucks going and the flyback. Quiescent current draw, about 2 watts. About 2 watts. We're about to load this thing. We're about to have a proper party. And so the fun thing is this Zener right here. No, not those. This Zener right here. Let me zoom in and focus on that. I want to show you guys what's going on here. Wow, those lines on the screen, no idea what that's about. I am super sorry about that. There must be some weird shadows going on. I have no idea what that's about. They do not exist in real life. Yeah, witchcraft. So yeah, these couple diodes here, basically there's an 18 volt and a 8.2 volt. And they come back and they tell the PWM controller when we want more or less oomph. And so when we do our line and load regulation tests, if we see that this rail is dropping out, that means we might need to tweak something. But so for an idea to see what we're asking for, let's take a look at that feedback pin. Because the feedback pin is a combination of the output of this optocoupler and did I actually not break that out to a test point? That's a shame. It's got ground over here, and feedback's coming over yonder from ooh, power OK isn't illuminated. That's weird. Yeah, thanks, man. I put a lot of time into analyzing this one. I think our PWM, I don't think we're hitting our high threshold. I think that the flyback should be regulating this bus up to 18 volts. Yeah. No, 8.2 volts should give us power OK. What? What's going on? Hopefully I just put the diode in backwards or something goofy. So we're putting 500 millivolts across the LED. It's not 0. So this is coming We're biasing. So the intention is that, okay, so we got a 5 volt there. So we're passing almost no current. We're passing no current through that opto. Why is that? Let's take a look over here. Got a 15 volts present there. 15 volts present there. Why is that? Because D48 has D48 is an 8 volt zener. What do we have across it? Sorry, I'm thinking. I'm doing a terrible job. Hey Dave, how you doing? Welcome to the stream. Debugging why our power OK indicator did not illuminate. It's bizarre. Because here we've got 15 volts on the top end of the zener, 8 volts on the bottom, so we're dropping about 8 volts across the zener. For some reason when I measure the zener directly, I'm not getting any of that. That's what's driving me nuts. Even got like, oh, I bent my scope. Man, that's what I get for buying cheap leads. Yeah, that's bizarre. Anyways, so we keep on measuring. Back to ISO ref. We got 0.5 volts applied there. So it seems as though either our transistors borked, because we've got 7. Wait a minute, we got 7 volts applied to a BJT? Something ain't right. That BJT should be super, super on. I'm betting Q16 is populated wrong. Q16 should be a 3904. I'm betting it's not. Let's swap it out. Want to place bets? Yeah, I don't know. Either I overheated the transistor, I put the wrong one on the board. For some reason, I'm not confident that all my 3904 or 3906s are right. In fact, I might just replace them all. But Q16, why not? I'm already doing it. Replace Q16 and Q15. And yeah, there's a couple ICs that, or a couple of those little transistors that I cooked. But the fact that we just allegedly saw 8 volts. JD's like, yep, went back, looked at the archive, that one got hot. Yep. This is where the T12 soldering station is gonna really flex for us, right? Okay, we got 3, 2, 1. I bet it can already melt solder. This thing gets hot fast. I love it. Alright, I don't know if I can get these off without the header gun. 3 terminals I could probably do, but Q16. Being careful to not overheat the optocoupler. We'll add those to our pile of sad transistors. Alright. Looking at that part more closely, we might have just had a bad solder joint. Leading to the optocoupler, one of the pins looked a little sad. But that shouldn't have affected the VBE. That should have still been fine. How much did I pay for it? Oh, for the solder kit? The solder kit? This one was, I think it was like $50, but it came with 3 tips. So, yeah, I liked it because it came with the tips out of the box and it was off Amazon. Actually, I think there's a link in the description. Again, I don't necessarily recommend this kit because they don't, actually I definitely don't recommend it unless you're willing to modify it yourself, because they do not ground the metal chassis. So if one of their very anemic wires comes loose in there, it'll like, yeah. I agree. I don't feel bad about replacing this little part. Cool. Alright, let's replace it. Alright. Looks like she still doesn't work. That is weird. Let's keep probing. Q16 pin 3 to ISO-ref. 15 volts. Whoa. What? D30? Did I just put that resistor back to ISO-ref? Did I put that LED across the wrong? I better not have. What in the world is that? That should not be a thing. Okay, I'm just gonna do this. We're just gonna short this thing to ground through the ammeter. We're gonna tie the 2 grounds together. I might have just goofed up where I put that LED. No, that doesn't fix it. That's super confusing. Okay. Alright, so there we got resistor 15 volts. Let's for a moment bypass this transistor. Let's just make sure the LED turns on when we bypass the transistor. Yes, indeed. When we forward bias the transistor, the LED will turn on. Let us attempt to forward bias the transistor manually. Being very careful to put this on the right side. Interesting. Q16. Oh my goodness. I never tied the emitter of that transistor to ground. What? What? Why? It's in my schematic. Why didn't that throw an error? Make it to the market. You call this the market? This is a rough prototype, man. Yeah, for some reason. There should be a via dropped. Because this whole plane is ref underneath. Why? Why you no via? Alright, so there's a couple reasons why this might have happened. I actually intentionally ignored some DRCs. No via to ref. And oh, I see it. I absolutely see it. Okay. So if you look at the schematic, these are tied to ref. Everything else is a named net called ISO ground. They're actually tied to different nets in my schematic. That is absolutely the problem. Okay. Well, let's fix that. We can add a wire for that. And the reason why that happened is because the solder kit. Yeah, so it has chassis ground, it's just not tied to the chassis. Yeah, it's ridiculous. They have a fuse and in the power entry module on the back, at least they got that right. But yeah, so I'm gonna go in there and I'm going to mod their kit. I'm gonna mod their kit to fix it. Wow, so these are isolated from each other and from this reference. That's insane. Okay, we're gonna add a couple bodge wires and hopefully we'll see this thing come to life. Okay, bodge wires. I haven't needed those in a while. I wonder where those ended up. There we go. An appropriately black bodge wire. Just using some old telephone wire here. Excellent. Where do I find that schematic? Yeah, I actually haven't released this. I should. What I'll do for you is I will zip this up and I'll put it on our Google Drive and I'll drop a link so you can take a look at what we're doing. Yeah, so this is a subset of our UPS design. So basically we just grabbed some critical circuits from a bunch of different daughter cards and tied it together. Man, I'd say I can't believe I didn't see that, but I threw this schematic together real fast. So I'm not terribly surprised. This didn't get a whole lot of review. Well, this got no review. I just kind of threw it out the door. I was like, it's cheap and it doesn't need to work 100%. Just needs to work like 80%. Yeah, I'll definitely make sure this schematic gets out so you can see it, JD. It's a fun little board for sure. I think you will really get a kick out of the way that we implemented feedback for this supply in particular. Alright. There we go. So now we've got one of those tied to ground. That'll probably help. And I'll do a shorter one to get the other side tied to ground. I'll be very curious to see how the feedback behaves, because we were seeing that one voltage that didn't look quite right. I wonder if that'll look a little better now. I hope it does. Oh, this is way too long. Yeah. Wired phones. What are those? Yeah, it's I just like it because it's a solid core thin gauge wire that you can, yeah, just kind of works. Wired phones are obsolete, but that doesn't mean the wire's bad. Wire's fine. Okay. So we'll get this wired in. We'll do some line regulation, load regulation, and if we find any issues, I might have to tweak those offline, but we can definitely get through a proper suite of tests before we call it today. Just might need to save some of the debug. Alright. So maybe those transistors were fine after all. But you know, it doesn't seem fair to do line and load regulation testing when, like, you don't even have feedback implemented. That was just running open loop with a fixed PWM limit. Alright. Power back on. Hey, power's okay. Look at us go. Got indicator lights and everything. Oh, that's awesome. Sweet. Very happy to report it appears to be functional. Let's check on those 3 voltages now. So we've got the reference to 15. Ooh, we're only seeing 12, 13 on 15 now. Seeing 5 volts on the other one, and I bet the reason why is because we're not getting enough energy through our flyback. Yep, we're only 14 volts on the flyback, which means that our fixed frequency limiter over here that's built between, what is it? It's built between R114 and R108. So let's change that 2K15 for something a little bigger. R114 is getting a little bigger. What do we have? What do we have available to us in our kit of parts? We need to go a little bigger than 2.15. So the next size up we have is 402. Sure. What could possibly go wrong? We should still be able to tug around on the feedback should still work and limit the peak power. So we're going to put in a 402K resistor. I'm just going to mark this up. Wait, no, this is a 4.02K ohm that we're populating in its place. R114. Yeah, I figured we might have that. Basically, it just comes down to, right, there's some losses. I picked our duty cycle limit based on what would be required, ideally, to get our full output power. Looks like, for one reason or another, our transformer is not performing quite as well as the calculation suggested it should, which is fine, you know. I wasn't perfect when I wound this. I wound it by hand. It was my first time winding the transformer with this method. It is very, very possible that I screw that up somehow, you know? Cool. Plus we added the feedback tug. So, hey, let's turn this back on. See how she looks. Should be running at a higher duty cycle. And let's check out her 15 volts. Let's see if she came on. 15.08. Oh, you can't see that. Oh, I'm the worst. Here, let's zoom out a little. There you are. So ISO ref. We changed out that resistor. Now we're getting a proper 15 volts. We're getting a proper 5. And are we seeing something closer to our 18? We should be seeing something close to 18 volts on this intermediate node. What? Sorry, on this intermediate node. Yeah, there we go, 18.33. What is up? Oh, what is up? The design is totally working. Totally working. Our quiescent power is up a little bit, but we're actually at the right output voltage, so I'm not gonna get too bent out of shape about that right now. I'm gonna just let myself be excited about how the design's working. Okay, scope probe time. So we'll see how this works compared to last go around. We have a new camera. What? Just for looking at this scope. It's a little fisheye-y. Oh boy. You can see the white paper in the reflection of the screen. Hopefully that's focused okay. I bumped the camera so our focus isn't perfect. I'll scoot it till it looks pretty good. The function of those gaps, that is to establish isolation. So that is a property called creepage and clearance. So basically there is an amount of distance straight across from two conductors across an air gap that'll arc over and break down your isolation. When you're going along an organic surface like this, like FR4, it can actually creep around those edges. So I'm establishing an air gap and forcing the electrons to creep around it, thereby establishing a larger creepage distance. That's creepage and clearance is the keyword to Google if you want to look into that more. Alright, so I'm going to get this hooked onto our ISO ref. We're going to get this hooked down to 15. Oh, we were just going to do line and load first? Okay. Guess we can do line and load first. But hey, may as well show you what's going on. Trigger level. Look at that. So this is AC coupled 500 millivolts per division. Looks like we got some noise, some switching noise. But by and large, it's not so bad. If we load down the converter a bit, just a touch, nothing enough to scare you. If we load down the converter a touch, wonder what we'll see. I bet you it'll take some of that noise right out of there. Whoa! When I loaded that supply, we fell out of regulation. Alright, I gotta show you that on the main cam. So I loaded down the 15 volt rail. We fell out of regulation proper. That's a shame. Yeah. Whoa. Come on now. There we go. Got a probe on one end. Stick this on the other end. Oh, wait a minute. This isn't isolated. Ground is ground. Oh, it is isolated. Good. So I just wanted to take a look at how our gate drive's looking. So you can see the flyback clamps doing their job. Oh, you can't. Sorry. Now you can see the flyback clamps doing their job. There's some sinusoidal ringing underneath it, but that's okay. Nothing that'll blow anything up. Looks excellent. And if we drop this on, look at that, it adjusts the duty cycle. Looks like we need to make it more extreme though. We need to be able to pump more power through this thing. So I need to set our default duty cycle a little higher, even higher still. I have to do some analysis on that. that's okay. We'll just take the measurements and we'll see how we do. Gonna pull one of our meters out of here. Gonna get this in the amp range. Maybe we'll do. We're not pulling a ton of current. But I'll just measure it like this anyways. Right, this does nothing. We need this to go back to ISORef. It's weird. Isolated supplies, man. Cool. So we're gonna go over to our 5-volt rail. There we go. So we're getting what are we getting here? 38 milliamps. That is not a lot. And how is our I have a feeling our line regulation is not doing so hot. Oh, actually we're still at 5 volts. And oh goodness, our 18-volt rail's down to 11. Oh yeah, we're never gonna get this thing up to power. This thing is going to totally fail. Yep, before we get up to power. So I loaded it a little heavier now. Our output of the Flyback is at 9 volts. Oh goodness. Let's see if we can get this thing up to a higher current. We're at 77 milliamps. Oh, come on, man. You're killing me. Alright, there we go. We're getting 100 whole milliamps out of the thing. Okay, so it's clear that I have some refinement to do here. We're not going to be able to complete our test today. That's okay. That's fine. I concede. But what's more important than that is that the premise of the design is there. Like, we are able to get the energy across in the Flyback. We're able to get it across. We need to tweak the feedback network. We need to do some math, set our default duty cycle a little higher, get some more energy across so we can actually load the thing. That's what this prototype's about. I'll tweak those values. We'll chat more about this next week. Yeah. 90 milliamps on the 5-volt rail is more. We're supposed to be able to get a 1/4 of an amp off both of these outputs. And some of our supplies actually need it. So I know that the transformer can provide it. Let's just quick gut check. Yeah, this is barely even warm. Our transformer's got a lot more oomph. It can give us a lot. So, before we go though, before we call this a day, I want to take a look at the ripple voltage on the output of this thing with the scope. So we'll just kind of let it, we'll do a light load, I guess. I don't want to overburden it, but we'll give it some load. We'll give it enough that our Flyback rail is still doing something. And we're just going to probe the output of the Flyback. That ain't right. Absolutely no way that's right. Okay, so ref. That looks incredible. (200 nanoseconds). Where is our switching noise? I want switching noise. What is this? Right, we're gonna have to zoom in. There's our switching noise. Excellent. Zooming in a little more. Hey, you can see that now. Oh, dope. Yeah, it's probably the 50 hertz cancellation stuff. So now you can clearly see that slope. So that is, we're getting a shot from the flyback and then we're coasting down. This is the output voltage on the 15 volt rail. We're getting a shot of energy from the flyback and then we're coasting down. And then a shot of energy from the flyback and then we're coasting down a little bit. So this is in 200 millivolts per division. That is, wow. Okay, so it looks like a little bit of refinement might be required on the output. That is a big voltage spike. Ah, no problem. See, you tested. I don't mind you came in late. I'm just happy you made it. Yep. So that is pretty neat. So maybe this diode's being a little slow. Whoo boy. Yeah, there's a lot of ringing there. Maybe we should have a snubber on the output. I'll have to take a look at what I want to do with this. You can clearly see our pulse of output and then a bunch of ringing. Then our pulse of output and then a bunch of ringing. I mean, it is a flyback, but still, that I might want to refine that a little more. So, we'll see. I'll play around with this a little bit, and we'll get that trimmed up. But it's good to know that the duty cycle that we're running at is basically 0. Like, if we set that default duty cycle better, we can get a lot more power. I bet just setting that default duty cycle right will totally fix the issue. So, I'm just glad to see it didn't blow up, right? Dang! While we're in here, let's capture the turn-on transient for the supply. Right? Maybe we need to zoom out a little more. Coupling, DC, single, turn it on. That's fun. That is super cool. You can like see it turn on, the load turns on, then it finishes coming up the rest of the way. What if we do an unloaded turn on? Oh, that was an unloaded turn on. Wow, that's scary. There you go. That doesn't look so bad. I like that. Let's check out the 15 volt. Turn it off. Single shot capture. Turn it on. It's not so bad. And the 5 volt. Oh, trigger level too low. Alright, any final thoughts? Anything? Oh, to plot? That looks awesome. 5 volt turn on, super controlled. That is super cool. Yeah. I don't know, it was awesome hanging out with you guys. It's a shame this keeps kind of doing the same thing where I've got all these tests planned and I can't get through them all. So here's what I'll promise. Next time, I will have the circuit assembled, all the tedious parts. We'll just do the fun controllers or anything like that together. We'll do the fun stuff after we finish the testing for this converter. Hopefully you have a little bit of satisfaction from seeing it power on. We get the 15, we get the 5. We can load it. It doesn't burst into flames. It just can't output quite as much power as we were hoping. Oh, Dave, happy to have you. Happy to have you. Yeah, I hope you can join us again next Saturday. We'll be doing some good stuff. Just so you guys know, next stream will be on October 12th. Super pumped. We got some cool videos coming. So definitely hang around the channel and sign up for that sticker giveaway if you didn't yet and you want a sticker, because they're pretty cool. But yeah, just really appreciate y'all taking the time to watch today. It's been an absolute joy hanging out with you in the shop. And hey, we got to celebrate just a little bit of success, right? Here we got an isolated 15 volt regulator. We've got our dual input going on over here. We've got our 3-buck converters. This is starting to look like a proper system. That's pretty exciting. Yeah. Yeah. So yeah, look forward to seeing the comments. I will remember to put out a link to this schematic in the next day or so. I'll make sure this gets out there, and we will run through the rest of our tests. Really appreciate everyone. See you, JD. See you, WTP Gaming. I think Tested already left. See you, Dave. Hannes. It's been an absolute pleasure. Talk to you guys soon. Bye.